Hello and welcome to this video for Chemistry 30 in the Organic Chemistry unit. In this video, we are going to finish up naming organic molecules, looking at the final two that we have to complete, which are carboxylic acids and esters. So just a little preview at what carboxylic acids could look like. This is a diagram of butanoic acid, and this is a diagram for my ester, ethyl butanoate. Okay, so we're going to learn again how to identify them, their properties, how to name, and how to draw them. So starting with, my notes are out of order. There's the carboxylic acids. Starting with carboxylic acids, they contain, when you look at the formula, the simplest organic acid you can have is it would actually be HCOOH, okay? So you have COOH in your formula. This H is the the H bonded to the C. Because my functional group is carbon double bonded to one oxygen, single bonded to another oxygen that's bonded to a hydrogen. So there can be an H on here making my simplest carboxylic acid, or there could be a longer carbon chain. Okay, so R again in this formula can be a carbon chain or ring, or it can just be hydrogen. This is called the carboxyl functional group. So in your formula, when you see COOH, that is a carboxylic acid, also known as an organic acid. This hydrogen here, which is this one here, being the donatable hydrogen when you have it reacting in water or whatever the case is where it's donating its hydrogen. Now they are still considered saturated because the carbon-to-carbon bonds, if there's multiple carbon-to-carbon bonds, they are all single in these molecules, okay? So when carbon-to-carbon bonds are single, that means the compound is saturated. Also, the double bond in part of the functional group to the oxygen is not taken into account as being something that makes it saturated or unsaturated. It's the carbon-to-carbon bonds that we're focusing on. Okay? Some of their properties, they are going to be soluble in water no matter their size. Remember with alcohols, it depended on their size. With acids, no matter their size, that's a big polar end, that carboxyl functional group. So it will be soluble in water no matter what. It also has London dispersion forces. So it has all three forces, making them have the highest boiling point out of all of your molecular organic molecules. Okay? They are acidic but weak acids, right? They're not part of the strong acids from the last unit, if you remember. So diagnostically, they will turn litmus paper red. They will react with metals to produce hydrogen gas very slowly, and they will neutralize bases. Some uses of them: rubber, vinegar, rust remover, fruits. A lot of fruits, as well as food preservation. A lot of fruits and things like vinegar are going to have be an organic acid, like citrus acid and so on. When you name them, the carbon of the carboxyl functional group is always at the end of the molecule, and that is always numbered carbon 1. You then give it the same name that it has as an alkane or a cycloalkane, it could be. You drop the E like we did with alcohols and add oic acid. But unlike alcohols, you don't need a number where the oic acid or the carboxyl functional group is, because it's always carbon 1. That's always at the end as carbon 1. Okay? So for example, when you have your simplest molecule, simplest carboxylic acid, the formula again is HCOOH. Okay? The name of this, because there's one carbon, is methane. Like methane, I drop the E and add oic acid. So methanoic acid. This is the first type of organic molecule that we have where it's actually two separate words. The acid is separate from the methanoic. Okay? If you see a line diagram, remember the lines that go to an element or a group of elements don't have carbons, but the other corners and ends of lines have carbons. So there are 2 carbons, and again, I would number it from the carbon at the end with the carboxyl functional group and then go outwards. Okay? So this would be 2 carbons, which is ethanoic acid. Ethanoic acid. Okay? Let's look at when we have branches or the benzene ring. Okay, when you have the benzene ring, this again is carbon 1, and the benzene ring is part of the entire structure or parent, if you want to call it the parent. The name of this is benzoic acid. Okay, just like when you had the hydroxyl functional group, an alcohol on your benzene ring, it was called phenol. This is one whole parent called benzoic acid. Okay. Now I'm going to get into a branch. So this is my parent is still the longest continuous chain, but it has to be the longest continuous chain that contains the carbon that is double bonded to O and single bonded to OH, and that is carbon 1. Then I find my longest continuous chain from that, number it outwards, and then here I would have a branch right there on carbon 3. And as we know, a 1-carbon branch is called methyl. So to name this, again, start with my branches. On carbon 3, there is a methyl branch, and my parent is 4 carbons long, so that would be butanoic acid. Again, I don't need a number where the carbon is that has the carboxyl functional group, because that is always on carbon 1. So it's just 3-methyl, make sure we got that right, 3-methyl butanoic acid. Okay, so those are your acids. Next, we're going to get into esters. These are the final organic molecule that we look at in Chem 30. Keep in mind there are a lot more molecules, but for Chem 30, this is as far as we go. Now, esters might be the hardest ones. To understand an ester, it is the combination of a carboxylic acid and an alcohol joining together. Okay? So I'm actually going to show you this process so it'll make a little more sense. It's very similar to a carboxylic acid where it has C double bond OO, but the H that was on the acid has been replaced with a carbon chain. Okay? So there's no hydrogen on that oxygen, there's another carbon chain. This is R prime, just means another carbon chain different from this part of the carbon chain on the other side. So we commonly separate this into 2 halves, and I say that this is my acid side. This is the remnants of my acid that lost its hydrogen, and this is the alcohol side, the remnants of the alcohol that joined with the acid. Okay, so let me show you this reaction. And we are actually going to get into reactions later on in this unit, so it's not a bad thing to get into. So let's say I have 2 carbons in my acid. And like we just learned how to name this, this would be called ethanoic acid. Okay, it is going to react with an alcohol. In this case, let's make it our simplest alcohol that we can have, which is methanol. Methanol. Okay, now what's going to happen? Actually, I'm going to draw this a little differently. It's the same thing. I'm just going to write the OH on that side. Okay, because what's happening in this reaction is the hydrogen comes off of the acid and the OH comes off of the alcohol. Okay, they come off. So this is lost with that, and they actually form a molecule of water, right? HOH would be, I'm going to have to write my other product up here, my ester product. Okay, so that would be a water molecule that comes off. Now, when these are gone, This is gone and this is gone. This leaves my O needing to bond to something and this C needing to bond to something. So they bond to each other like that. And so this is what my ester looks like. There was 2 carbons from the acid side that stay the same, but now this is bonded to the 1 carbon that came off of the alcohol. Okay? So again, if I write what they were, this was OH, and this was my hydroxyl functional group on my alcohol. The H comes off here, the OH comes off here. Okay, they make water, and this is your ester. Okay, I can actually tell you the name of this ester, and we'll get into how to name them. The name is going to be called methyl, as a separate word, ethanoate. Okay, so the methyl comes from the alcohol side. There's 1 carbon in it. Separate word, you name the acid side and change it from oic acid to OH. So methyl ethanoate. So it's kind of almost you're naming it backwards from how it's drawn. This is the methyl side. This is the ethanoate side. 2 separate words. Okay? Now they are also considered saturated again because all the carbon bonds in the ester are going to be single. Properties, they are polar, but their solubility again depends on their size. Okay? Because this part of the ester is polar, but if you have long carbon chains going outwards on both sides, those are nonpolar. So it kind of, although it remains polar, it might not be polar enough or have strong enough dipole-dipole forces to be considered in water. Plus, they don't have hydrogen bonding. That's also another key too. Okay, so although they have London dispersion and dipole-dipole, their polarity depends, their solubility depends on their size. So small esters again are 6 or less carbons in total. Large esters are 7 or more carbons in total. Okay, so small will be soluble, large will not. Now their boiling points are going to be a little bit lower than carboxylic acids and alcohols because they do not have hydrogen bonding. At the end of this lesson, we'll actually do a review of the compounds and their different properties. So they also, very similar to aromatic compounds, give off aromas. Different flavoring agents that we use are esters. When you're naming them, like I said, you name the alcohol side first and change it to almost like it's a branch where you give it an alkyl name, and then identify the acid that it came from, drop the oic acid, and replace it with OH. So if it was butanoic acid that was part of the ester, it becomes butanoate. Then again, you put the 2 names together with a space between them. So methyl butanoate, it's hard to see, but there's a space between these. Don't put them together as one word. Okay, so methyl butanoate would be the butanoate. You can kind of think of it as like the parent. So there's 1, 2, 3, 4 carbons in it. It's double bonded to an oxygen, single bonded to another oxygen. So that's the butanoate part. Okay. And then the methyl part is the alcohol side, which is this side here, which methyl would be 1 carbon. Okay, I do need to finish to make my 4 bonds around everything. Don't forget to always have 4 bonds around everything. And when you're numbering these, and you can have branches on both sides. Okay, so this is carbon 1. As you go outwards, the number increases. That again is your acid side. On your alcohol side, you start 1 and name outward if there was more than 1. Okay, so we will look at examples of naming these, but this is just your early little heads up. Okay, so here's another example. Again, I like to say, okay, this is my acid side, sorry, and this is my alcohol side. You don't have to do that, but it just helps me with naming. I am finding the longest continuous chain on my alcohol side and on my acid side, okay? Starting with the carbon double bonded to the oxygen, that's my acid side. Starting with the carbon bonded to the oxygen on my alcohol side. So those are my two longest chains, and again, they can both have branches on them, okay? So I number 1, 2, 3, 4 for the acid going to the left, and 1, 2, and so on for the alcohol going to the right. Now I name the alcohol side first. The alcohol side is called ethyl because there's 2 carbons in it. I put a space, and my acid side is butanoate. So the name of this is ethyl butanoate. Okay? If I look at a line diagram, these lines go to oxygen, this double line goes to oxygen. So my carbons, there's a carbon, 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 carbon. There's actually 3 carbons on both sides. So the name of this would be propyl from my alcohol side. There's 3 carbons. And my acid side also has 3 carbons. So it's propanoate. So the name is propyl propanoate. Okay? Now let's get into some branched ones. So again, start by separating your acid and your alcohol. Find the longest continuous chain on either side, starting at the O. So that would actually be my longest continuous chain on my acid side. This would be my longest continuous chain on my alcohol side. It's like you have to start at the O and go outwards. The O obviously doesn't count as a carbon, but you have to start like that on each side. Okay, so that means this is a branch and this is a branch on the alcohol side. So if I were to number this, again, I start at the first carbon bonded to the oxygen in the middle and go outward on both sides. Okay. Now I name my alcohol side first. This again was the alcohol side, and this is the acid side. So on carbon 1, there is a methyl branch, and this whole side is the ethyl name, right? Because the alcohol changes to an alkyl name. So 2 carbons is ethyl. Now, technically, we actually don't need the 1 here because that's the only spot a methyl branch could be. Because if it was on carbon 2, it would just become part of the longest chain on that side, and this side would then be called propyl. Okay, so you don't actually need the 1 there. It's just methyl ethyl. But if you put the 1, I wouldn't take a mark off because, again, you're kind of new at learning how to do this. But in an answer key, you would not see a number there. It's just methyl ethyl for the alcohol side. The acid side, I do need to say where the methyl branch is because it could be on 2 or 3. If it was on 4, it would become part of the parent again, and that would make it a 5 long carbon side. Okay, so on carbon 2, there is a methyl branch on my acid side, which is called butanoate. Okay, so methyl ethyl for the alcohol side, space, 2-methyl butanoate. All right, put up the answer, make sure we got that right. What did I do wrong? Oh, I edited my notes and I forgot to edit the answer. Okay, I put a branch on the side which didn't have 1 before. So methyl ethyl 2-methyl butanoate. Okay, so that is how you name esters, the final compound. Now, before I finish the video, I want to do a sample diploma question and get into some of the properties of the organic molecules. We've talked about them, but I want to review them. Okay. So first of all, when you're given diagrams and you're given a question like this, it's asking you to find an aromatic, an acid, an unsaturated aliphatic, a halogenated hydrocarbon, and so on. First thing you want to do is identify if they are aromatic or aliphatic. If they have a benzene ring, they are aromatic. If they don't, they are aliphatic. Okay? That's your first categorization. So number 2 would also be an aromatic because it has benzene rings. Aromatic. And 4 would be aliphatic because it does not have benzene rings. Okay? So oh, I definitely spelled that wrong. What happens when I talk and write? Aliphatic. Okay? So that's your first categorization. Aromatic versus aliphatic. Next are saturated versus unsaturated. You're looking for carbon-to-carbon double and triple bonds, carbon to carbon. The benzene ring has carbon to carbon double bonds, right? Because remember, that's what the benzene ring is, alternating carbon to carbon double bonds. So aromatics are unsaturated. Unsaturated. Here, my carbon to carbon bonds are single. The C double bond O does not count for saturation. So this one is saturated. The carbon to carbon bonds are single. The next one, though, I have a carbon to carbon double bond. So that makes it unsaturated. Okay? Not that double bond, the double bond between the carbons. Okay? Halogenated. If there are halogens on them, they are halogenated. Now, if I were to also identify these molecules, so we already identified the aromatics. This one has C double bond OOH, so it is an acid. This one has C double bond OO, but no H. There is a carbon branch on the O where the H was. So that is an ester. Okay? So those are identifying first your compounds. Now we can match them. Now if it said you could only use every number once, the aromatic, because one of them is the halogenated hydrocarbon, the halogenated hydrocarbon has to be number 2. That's the only one that's halogenated, so that would be our last number. So that means the aromatic that we're going to put for our first number, if we can only use every number once, would be 1. Okay? The carboxylic acid, we identified the acid, that was number 3. And the unsaturated aliphatic. The unsaturated aliphatic was the ester, number 4. It's only unsaturated again because this ester has a double bond between the carbons. Usually esters are not unsaturated, but the carbon chain has carbon to carbon double bonds. So that would be number 4. So your answer would be 1, 3, 4, 2. Okay? If you could only use every number once. If you could repeat the numbers, your first one could be a 1 or a 2 because they're both aromatics. Okay? Now, you do want to know some of the following physical properties of organic molecules. We've talked about their solubility. Conductivity, they're all molecular, so they don't conduct, with the exception of acids, because the carboxylic acids are weak acids and they will weakly ionize. Okay? We talked about their reactivity through each compound. Viscosity and density have to do with like the thickness of the compound. The thicker it is, the stronger the London dispersion force is, right? That's going to make it a higher boiling point, for example. The thicker it'll be because the molecules get attracted more to each other, so they're thicker and denser. Okay, solubility, again, I'll actually go through the solubility and the boiling points in a little bit more detail in the slides. Now, I mentioned a term with you guys before called hydrocarbon derivatives. If I go back here for a second, a hydrocarbon derivative is a molecule that has more than just hydrogen and carbon. This molecule here only has hydrogen and carbon. So it is a hydrocarbon. Okay? But this molecule has bromine, this one has oxygen, and this one has oxygen. Those are your hydrocarbon derivatives. They have more than just hydrogen and carbon. Okay? The other term you're going to want to know for your unit test is homologous series. A homologous series is a group of compounds that are in the same family, but they have a different number of carbons and hydrogens. Different number of carbons, and obviously if their carbons are different, their hydrogens are different. Okay? So, for example, if we were to look at ordering everything in order, actually I'm going to go back here for a sec because it's not going to be in this example. If I were to look at a homologous series, let's say I have a group of alkanes. Okay, so I have CH4, C2H6, C3H8, and so on. Okay, this is a homologous series. They are all parts of the same family. They're all parts of the alkane family. Again, we know they're alkanes because their hydrogens are double the carbons plus 2. You could also draw them, but that's how you know by the formula that they're alkanes. Okay, so this is a homologous series. The boiling point would increase as you go across with more carbons, because remember, when you have more carbons, you have more electrons, and more electrons makes it have a stronger London dispersion force. Okay, same with the viscosity and density. They would be thicker as you go across and more likely to be, this is a gas, for example, the more carbons you have, more likely they turn into liquid and even solid. Okay, so that's a homologous series and how you order them within a homologous series. But if you want to order them with different functional groups, that's where this comes in. Okay, and so we have the lowest being any alkenes in a list, then alkanes, and finally alkynes. Remember, alkynes were at the top just because of their linear structure. It gives them more surface area to interact. Then any aromatics and halides, depending, of course, if they're polar or nonpolar. And then your esters, alcohols, and acids are the highest. Okay? So these are all your nonpolar molecules. Usually, halides again depends on if all the terminal atoms are the same or not. Usually these are the only nonpolar ones, so they only have London dispersion. These are all polar. Okay, but these two here have only London dispersion and dipole-dipole, whereas the last two have all three of the forces. Okay, so all of these were polar, but only halides and esters have London dispersion and dipole-dipole as long as the halide is polar. The alcohol and acid also has hydrogen bonding. Okay, so when you're given a list of molecules, you basically have to memorize this. This is the order of your boiling points. Now, let's say I'm just testing you on this, and you're just ordering the following groups from highest to lowest. Okay, so my acid would be first, then my alcohol, then my aromatic, then the alkane, and finally the alkene would be the lowest. That's not usually the most common question you're going to have, though. You're usually going to be given molecules to put in order. So you have to first identify what group or what functional group or type of compound you have. So again, you want to memorize the generic formulas. If your H's are double the carbons plus 2, that means you have an alkane. If you have OH written in your compound, that is an alcohol. That is the hydroxyl functional group. If you have COOH written in your molecule, that is the carboxyl functional group, making that a carboxylic acid. And then the last one, I only have double the hydrogens of carbons. That is an alkene. Okay, so ordering these from highest to lowest, again, my acid would be the first. the CH3COOH. Then would be the alcohol, C2H5OH. Then the alkane, C2H6. And finally, the alkene, C2H4. Okay? So when you're looking at the formula of a compound, that's going to help you to determine, again, what type of compound you have and then order it based on that order we just looked at. The other thing we want to talk about is solubility. So our insoluble organic compounds in water, this is again solubility in water. Remember again, solubility is like dissolves like. So although these are insoluble in water, they might be soluble in other non-polar solvents. Okay? So there is your list. So this is again insoluble in water. This is soluble in water. So having the same forces as water, okay? If they do or not. So the insoluble ones do not have the same forces, or they're large, so it neglects their polarity. Soluble will have London dispersion and dipole-dipole and hydrogen bonds. Or the esters and polar organic halides, they're not as soluble as the acids and esters, or alcohols, sorry, but they are still going to be soluble slightly anyway, depending on, again, the ester size and if the organic halide is polar. Okay? So that is it for this lesson. I'm actually going to go back and leave you with this chart here, which is a summary of all of the organic compounds. Now, I let my students use this on quizzes, but you're not allowed to use it on unit tests or the diploma. So this is essentially something you kind of have to memorize, okay? The generic formulas for everything, the generic parent naming system, an example with a name, how to identify the number of carbons in your parent group, and how to number the carbons, okay? The things that take priority in numbering, again, are double bonds and triple bonds, the hydroxyl functional group, and then when you have a carboxyl and ester, those have to be number 1. Otherwise, you follow the lowest branch sequence for the other compounds. Okay? So that is it for naming organic molecules. Thank you very much for watching this video.